Hello Chem 1B, this is Chapter 18, Lecture Video 2. And what we learned about in the last video is that really heat and time alone aren't the only components of controlling whether a process is spontaneous or not. And in reality, time really doesn't have much to do with it. It's all about thermodynamics that's going to control whether our reaction is spontaneous or not. How quickly the reaction occurs is really not going to affect whether the reaction is spontaneous or not. So kinetics really doesn't have a lot to do with this. Now, how do we figure out what's going on here? Well, we need to study spontaneous processes and see what property they all share. And what we find out is that when we do that, all spontaneous processes are more disordered or random in their final state than they were in their original state. This leads to what we call a new thermodynamic property known as entropy. And entropy, often symbolized by an S here, is a property that kind of is related to disorder or randomness within the system. So if a process is random, what type of mathematics should we use to model its behavior? Well, those of you that have ever, gambled, know that a large part of gambling is based on one type of mathematics, and that is probability and statistics, right? And so when we want to model random behavior, these are the types of mathematics that we're going to be using: statistics and probability. Probability suggests that a spontaneous reaction will result in the dispersal, or in other words, spread out of matter or energy, or both. Now, energy, this is our delta H portion of this. And if we want to disperse energy, we want delta H to be negative, some negative value, right? And if we want to disperse matter, this is going to be our delta S. And we want this guy to be positive if it's dispersed. And generally, if both of these two things are true, then we're definitely getting a spontaneous process. However, maybe one is positive, like delta S is positive and delta H is positive as well. Well, in that case, it might still be spontaneous if this guy outweighs this guy, right? Or so on. So we'll talk a lot about this as we go through. But first, let's keep talking about entropy, because entropy is the new thing. Entropy, again, symbolized by an S. Ooh, that's not a color there. Symbolized by an S. Entropy is defined as the number of ways energy or matter can be distributed, or in other words, spread out. Entropy is going to be related to randomness or disorder, but really only indirectly, because if you have a more disordered system, there's more ways to distribute energy than in an ordered system. The number of ways to arrange energy is related to the number of energetically equivalent ways to arrange the particles in a given state. Each way is actually called a microstate, and so you might see some of that vocabulary show up, and we'll see it on a later slide. And really, mathematically, we'll never use this equation, but this is equal to entropy is equal to K, which is Boltzmann's constant. It's this value. If you ever need it on anything, I will provide it, but you won't, because we won't use this equation. And W is really the number of ways you can arrange stuff. And you just take the natural log of the number of arrangements that you can have and multiply that by Boltzmann's constant. Now, that's all great and grand. Again, probably not going to be using this equation too much, if at all. But really, energy is something we'll talk about later. Let's start talking about matter dispersal, which is really what S is all about, our entropy. Let's look at our kind of example with the 0 delta H that I showed earlier. We have a flask, there's a gas inside this side, right? And we're going to open this valve and let the gas flow over to the other side. This is a more disordered system because the matter is now spread across the entire container now. There's more places it can be. So let's kind of talk about that in a little bit more depth. Let's say, for simplicity's sake, that there are only, I don't know, 4 molecules in that container. Then as long as the valve is closed, there's only one way we can have those 4 molecules present, right? They all have to be on one side of our flask, right? So I'm going to number these like, I'm going to kind of color these in, right? So we got this orange one, we got this red one, and we got a purple one, and we'll leave the other one as blue. Each one of these 4 different molecules or atoms or gaseous particles can only be on the left when this guy's closed. As soon as we open it, though, the number of ways we can distribute these 4 particles increases dramatically. It, in fact, increases to 6 different ways. This is what we call 1 microstate. A microstate is just the number of ways you can distribute the particles. So in this case, we only have one way to distribute them. They all have to be on the left. As soon as we open the valve, though, we can distribute them differently. And in this scenario, W would be 1, which means ln of 1 is 0. 0 times K is 0. So 0 entropy, there's very low entropy in this system. Okay, but as soon as we open that valve, the number of states dramatically increases, right? So if we color these balls differently, right? As soon as I open the valve, they're going to spread out evenly across both sides of my container here, right? And this is going to cause a number of different possible states to occur. Like so. And I can finish coloring all these in, but you get the idea. There are 6 total states that we could have where each molecule is in a different place in the container. The more ways of arranging it means the more disorder, and therefore the larger your entropy value in this system once the valve is opened. We have now 6 different states that are equivalent energetic states that our system could be in, which means W for our equation is 6, and we could plug this in. And again, this equation is not something generally we're going to be using. This is like the theoretical determination of entropy. And if you have to take, if you're a chemist and you have to take physical chemistry after organic chemistry, then you'll learn about this equation in much more depth. But at this level, it's just not worth covering. So if you guys have any questions, as always, please email me or come to the Zoom meetings, and I will see you there.